So good day to you all. In this section of video, we are going to discuss about the embedded firmware design and development. Right, already we have studied about what is a software, what is a hardware, and what is a firmware. So firmware is again a part of software, but like a normal software, we cannot change it very often, right? Something like the operating system of an Android system, right? So that needs to be stored in a permanent memory and it cannot be altered very often. So that is actually in between a hardware and software we can have the firmware. And most of these embedded devices, the program is going to be the constant one, so we are not going to alter the program very often. So what we can do is we can store all these the software codes for that embedded system. We can make it as a firmware and we can download this particular firmware while the system or while the chip is being fabricated itself, right? So that is not, that's not field programmed, but in the factory itself it is programmed. So that's called factory programming, right? And of course, using some special means, we can always update the firmware. Again, using this OTA, right, on the air transmission, you are uploading, you are updating your Android OS, right, operating system and all those things. So like that, firmware is in between the hardware and the software, right? So in this topic, we are going to discuss about embedded firmware design and development. The embedded firmware is responsible for controlling the various peripherals, right? So this firmware will be having the driver functions for all the connecting parts, right? It can be some different buses may be there, or different sensors will be there. And some sensors may be needing some linearization or some sort of signal conditioning, and all those permanent sections which need to be permanently there, right, which are not going to be altered very often, can be made as a firmware and can be available inside the chip, right? And the firmware is considered as the master brain of the embedded system. So this is equivalent to the software, right? So it is actually the master brain of the embedded system. And importing intelligence to an embedded system is a one-time process and it can happen at any stage. So whenever we use a hardware, it is going to be a permanent program, so we can't modify it. But if you are using a software, the software can comparably easy to modify, right? And most probably, since it's a firmware, so that will be programmed during the during the fabrication of that device itself, right? So most probably it will be done at only once. And it can be immediately after the fabrication of the embedded hardware or at a later stage, right? Most probably immediately after the fabrication of the chip, the firmware will be downloaded, and that will be almost, it is going to be fixed, right? We can't modify it unless or otherwise it is needed, fine. And for most of the embedded products, the embedded firmware is located in the permanent ROM, right? It's going to be a ROM, and they are non-alterable by the end users. Most probably we can't change it, right? And some of the embedded products used to control the instrumentation domain are adaptive. But there are some changes which are going to be adaptive according to the application what we are going to use. Designing an embedded firmware requires understanding of the particular embedded product hardware. So we have to get an idea about what is about the hardware, right? So what type of microcontroller used and what type of sensors and the final control elements or actuators are used, right? So what are the things available we have to mention is, like the component interfacing, what are the components that is interfaced to that, what about the memory map details, right? So what is the total amount of memory, how that memory is addressed. Again, it is memory mapped IO or IO mapped IO. There are two various of methods of addressing the memory. Then IO port, how many pins are there, whether that pin is having multiple functions, like whether it has an inbuilt ADC. And the configuration register details, how many general purpose registers are there, how many special purpose registers are there, and how to make use of these things. So all these things should be understood thoroughly before making a firmware. And the embedded firmware development process starts with the conversion of the firmware requirement into a program model using the modeling tools. Fine. And once the model is created, the next step is the implementation of the task and actions by capturing the model using a language which is understandable by the target processor. So again, a similar thing, like making the firmware requires, so what are the transactions that will be done using this particular microcontroller, right? So with which port I am going to take the data, and what type of driver should be available, which is actually, it's a bidirectional or unidirectional. So based on these factors, we can develop our own firmware, and once it is tested, and that can be downloaded onto your target processor or controller. The firmware design approaches for embedded product is purely dependent on the complexity of the functions to be performed, the speed of operation required, and all those things, right? And the two basic approaches are, one is a super loop based approach and the second one is embedded operating system based approach, right? So these two methods are widely used for the firmware development. The first one is actually the super loop based approach. So the super loop based firmware development approach is adopted for applications that are not time critical, right? So these can be useful for non-time critical applications, right? So where the response time is not so important and it's not so critical. And it is very similar to the conventional procedure programming where the code is executed task by task. Like whatever we write using your C program or Java program, so you will be having a collection of so many lines of code, and this lines of code will be executed line by the processor, right? So that is actually the conventional procedure for programming and the execution. So this super loop based approach will also be similar to that, where each and every step will be executed, or each and every task will be executed step by step. The task listed at the top of the program code is executed first, and the tasks just below the top are executed after completing the first task. So it will take the first task, complete it, then comes to the second task, executes it. Like that, the controller will be traversing through all the tasks that is available. And in a multiple task based system, each task is executed in serial in this approach. Of course, that we know that, fine. And the firmware execution flow for this will be something like, we have to configure common parameters, right? Say for example, for each and every hardware, right, most probably there will be some configuration parameters. I think whenever, you have studied something about microcontrollers, and for each and every driver ICs, you will be having a control word. So the control word determines in which mode the device need to be operated, whether it is going to be 16-bit or 32-bit, what would be the data size. So a few parameters need to be configured before application of any particular or any device in general, right? So the first step here is we have to configure what are all the parameters. So supposing I want specific input pins or specific output pins, right? Only this pin should be only used as an input. This pin should be used as an ADC input. So something like that. So if you want to configure some basic things, you can configure it, and that is actually the first step. Then the second step is start the first task and execute. Then execute the second task, execute the third task, and it goes on till the last defined task is executed. And once all the tasks are executed, again it will go back, because it's a super loop. So again it will go back to the first task. It will go back to the configuration section, and if any configurations need to be modified, then it will be doing it. Otherwise it will start from the first task and keep on executing that. And the order in which the tasks to be executed are fixed, right? So the task is already written and it's programmed, right? So you can't modify the order in which the task is getting executed. And since they are hard coded, right, already it's a one-time programmable, so it's already programmed, so you can't modify the execution sequence of the task. And also the operation is an infinite loop, right? So most probably I think you might have studied about the Arduino, Uno and all those things. So there is going to be a set of repeated tasks that will be executed in a loop without stopping. And this is the simple C program that shows the operational sequence, right? So here actually we are starting the program with the void main, and we'll be running the configuration, right? So in this when the first function is actually called as, all the configurations will be done, right? So which is actually input, which is actually output, and how much memory is allocated for different applications. So something like that will be done. Stack memory allocation, everything we have to do that. Then initialization. So suppose I want to use some pins, then we have to initialize some parameters, some values. Like again, we have to initialize the priority assignment for the interrupt controllers should be done. So some initialization part will be done next. And then once these two works are done, then there will be an infinite loop in which the task 1, task 2, task 3 up to task n, whatever may be the number of available tasks, that will be executed in a repeated loop infinitely. Almost all tasks in embedded applications are non-ending and are repeated infinitely throughout the operation, right? Most probably, right? As long as your say for example your washing machine is running, your microcontroller will be continuously executing the same task, whether the water level is there, whether the temperature is there. So that will be continuously monitoring the process. And this repetition is achieved by using an infinite loop, of course we have already discussed, and hence this name super loop based approach has been made, right? And the only way to come out of the loop is either the hardware reset or the interrupt. So either we have to do a hardware reset, so you have to switch off the total system, or an interrupt assertion, so you have to generate an interrupt so that the process sequence can be modified based on the interrupt level and the interrupt program. And a hardware reset brings the program execution back into the main loop, fine, and back into the main loop, fine. So again from the configuration everything will be done again. And an interrupt request suspends the task execution temporarily and performs the corresponding interrupt routine. So whatever the interrupt routine we have developed, that will be executed whenever that particular interrupt is triggered, right? And what are the advantages of super loop based approach? It doesn't require any operating system, right? So we are going to write a sequence of tasks, and this program will be executed. So the single program contains all the tasks. So multiple task assignment or multiple processing, no such worries will be there. So without an operating system, we can simply implement the super loop based approach, right? So there is no specific, because if you write so many different programs having different tasks, then which task should be executed at what time? You have to have an operating system which is going to initialize all these tasks, which will prioritize all these tasks. But since this is going to be a sequence of all the tasks, one by one it will be executed, it doesn't require an operating system. And there is no need for scheduling which tasks, again the same thing, right? So assigning priority to each task is not needed, and the priorities are fixed, right? Because each and every task will be executed in a sequence, right? Only after the first task, second task will be executed. Only after that the third task will be executed. So every task will be given the same priority. So there is no differential priorities can be done using the super loop based approach. Hence, the code for performing these tasks will be residing in the code memory without an operating system. So straight away you can program it using the code memory, and there is no necessity for an additional operating system image. And what are the applications of the super loop based approach? The first thing is, this type of design is deployed in a low cost embedded systems, right? Say for example, most probably again already we discussed, for low time critical applications we can very well go for the super loop based approach. Some embedded products demands this type of approach if some tasks itself are sequential.